First question. Oh. Yeah, sorry. Again, why the order parameter take it? Oh. So maybe. Yeah, okay. The question is, what's the general motivation? Maybe I'll go one step back and about the general motivation bundle. Like the first one we saw for the there, the goal is to describe a phase. And once you have this idea of order parameter, it goes from 0 at the third state and then the ordered state, describe the phase transition at the of the order parameter. Then we can make powers of now for the Ginsburg-Landau, we have this essentially tells us that it costs some amount to have this kind of, for example, for the case of the ferromagnet, we minimize locally the energy, just the magnitude. That curve. The other, so locally, point in as if my spin can point here, 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 direction. I need to add an extra energy cost, more energetically fuming to bend this spin with respect to the. So how many of you got the chance to? I think the first, I hope the first two exercises were okay. The first creative works and the idea of spontaneous symmetry breaking. I don't want to add trying to qualitate. For the second equation, some of you asked me not to verify what I say it's true, that the Pollock tangent. Any of you? Yes? Aha, okay. Okay, so there might be my issue copying and places because sometimes we define the A over 2 or A over 4 or B over 2. Yes. So I will correct that. That is. Otherwise, you should. Maybe they after what plane derivative. Or maybe there's okay, and the last two, I didn't expect. But I'm gonna comment on the and it, you're comfortable. Not give you a couple. Cool. Right, so last time we introduced the Landau function to describe a phase conductor complex. But we know from the beginning, since from the first class, that magnetic field acts in a non-trivial way in Superconductor. How do we add magnetic field? Not that field station. Now it won't directly density. How magnetic field. Yeah, but the order parameter is the electronic density out charge. How does magnetic like to reference for writing the energy function allow me to get that classical. That's what exercise. That's essentially called minimum. Instead of talking about momentum classically, A, where A is the vector potential, and just classical have a free electron. At this is through your own. So let's implement a quantum version of that too. How does it look? Now we have perimeter n. The original. Careful with use here. Let's for 2 add because take the derivative. This factor so we define. There will be a last term related to the energy of the electron itself, and stays the magnetic. There is some magnetic conductor. So as we did last time, can minimize functional back to the parameter value. But also because we know that the magnetic side of super has its life, we need to minimize this also how it adjusts that now. We'll get then two equations. First, we can minimize back to parameter. This guy, remember, type psi squared. So take now the functional derivative of psi. Terms are here. Things are funny because we have gradient of the here. Take then you have a function volume function gradient this function. Like our energy and density. Take function side like is tried to do is even the second one get it back to a function which itself is inside oh yeah. Right, so that is proposed as an exercise, and I already what you get. Following. Like a first now equation again I complex associating. Now the second again important. A is actually inside here. Is the rotation by the field, taking this derivative. Then on top of this, because now we have A with the result can it's a good exercise, so understand. Oh yeah, it's sub exercise of 4 because so I will write one step more. Just the so we get this gradient nation A, which the last term rotational exercise. The rotational. There is a now again and go back to actual rotational A. This is also from equations. Density, higher term. Back on density left. Just oh yes, derivative because I'm so if you have a complicated problem with boundary equations, solve then vector potential and how the really not an easy task. But so that's the equations you would get to solve the. Really get some knowledge out of this second equation. Find that say which actually bundle equations. So to do that, we are already inside the amplitude. I will get to. So start again. And the superconductor, we take the amplitude. And substitute here for the current, getting gradients of get I times phase with this y gradient of the plus here, and then we have the same. So let's say I have a macroscopic thing. I of here. So from here I get I times gradient. All right. Then I have superconducting. Remember we saw second lecture that I apply field penetrates and just a little bit on them. Just very tiny, the order of we think about as the rotation of field, as we the only place where I have field take the rotation very close to affect the upper current. Surface. That in mind, I can choose F decides such that I know that current associated of this position 0. So take now integral over this. Density. We have rho the loop in. Then we can arguments that actually specify this. The first is about the phase. Think about my wave function and take it the phase wave function valued. Phase can by n. Full of 2. For the second term, grow over line of integral of the rotational of over the associated. Have that 0, we have pi single valuedness. By that count. Making now surface integral. Again, whole integral flux. Oh, the density or change. So from here we get something. Yes, I was gonna comment that one comment on gauging variance. Planning not to talk about that. What we can see for form of the computation, there is some UET what I can observe is just always shift the vector potential by some gradient such that the self is left. But if I do that, change A, like I would change an observable. It's a bit problematic. Also, there is some how we define. There is idea of gauging variance related to the by the gradient of the same time. Yeah, but I'm not. I was so that yes. Because I can. Oh, this is yes. Yes. Urgence. Because you can completely eliminate gradient of gradient. Yes. Yeah, yeah, but this equation should start with already assume one would need to go back, or I change this. So now happens flux define actually the view out the box. Meaning flux have some very so note that this is a ring, so I have a whole space too. Flux the currents which are in the edges are applying the meaning just the flux whole actually, well, depends on where you define your loop. Chose to start with all has purpose of one could have taken a flux and left here, not just flux itself, but also flux externally applied field plus some spinning both of the just took this example to get rid of. So this idea of flux quanta things actually it looks like this. For example, if you have a superconducting surface there with is it black, yellow, round, really enough of them. Of course, the tubes of magnetic they interact and they get top view, that first picture on the view of is now standing around the superconductor. They can length scales being introduced last time. Lambda, which is penetration, defined essentially is get in conductor, but on the although and the other language tells us how areas you have also promised. We can take equation and in the gauge we started with. We can take the rotation. Rotational of gradient 0. Get rid of that rotation of A. So the definition that we is essentially the first. Second line came out looking I want you to take a minute now to appreciate this. We discovered superconductivity in 1911. 24 years, unreasonable assumptions, just based on electromagnetic, such an equation that phenomenologically, the 15 years for a person on the other side of the planet, pure orthogonal of phase transition, energy analysis, assuming, as again, looked unreasonable to get the very same. Times making assumptions a bit of the fact that we have to validate those equations. Assumptions feed the equations path they perhaps even beautifully microscopic theory we got from Dean Cooper 6 or the 7 years after, and that we can recover Landau from the. There are some unreasonable assumptions. Other parameters function. They decided to hold on to G because grasp without the need to get here with this. Oh, and then you can just take I think you can take the time. So we got the second. Essentially, So in phase transition without field, we actually see, for example, it is the transition to seed jump. So then you can get out ratios A over B. You also know TC. So jumping is unknown. If number. Yes. Yes. That's the ratio of parameter A related to appearance of fat. So essentially, PI is very much related to the coherence. Essentially, okay, any closed form that years after they derive. What is in those? It's essentially yeah, and how strong. Some flavor of break them, favorite. Yes. Expand hours. The actual terminology, assume PC course, you have the microscopics. I'll do next, talk about left-hand effect, and I might not have time, but if you understand left-hand effect, then does wonderfully conventional measure the extra go to materials and then some because the BCS was developed to describe this conventional computation, but the other parameter is a trop. Go to the microscopics, look at the electronic properties. Have a bunch of electrons, usually surface. Out of that conductivity. So the microscopic theory takes care of that, and potentially the non-trivialities. Doesn't need to be spherical. Really take as in. So that opens the door for a bit more complexity. So Josephson junction is nothing but junction is the nexus of two superconductors. In between them, you put then we can associate other parameters. Left side, right side, really think the wave function. One quantum Now if I put barrier between two regions of space, what's the first thing that comes to your mind? Quantum mechanics. Tunneling. So we're gonna treat now this barrier as called quantum mechanics. Electrons. Another. So I will boldly write your equation for lights. Let's say I put voltage here. That's the problem. They're symmetric. That those are the same. So also that this potential acts trivially in the sense that it just creates an overall bias such that the electrons which are on this side feel plus the potential. I would write this just keep my notation we just tell electrons here they are. Oh, sorry. Is it better now? Yes. And let's now add, again, rather ad hoc, that there is some finite tunneling between systems, meaning there is some wave function overlap, which will give me a number. Let's call it k. So we have those two equations. Oh, you can think really as, in some sense, of a wave function overlap. So the probability of one going one direction will be the same as the backward. Good. So let's yes, question. Why I don't have a kinetic term? Because I'm treating this as really as the wave function, which is static and just describing this bunch of electrons in one side of the superconductor. They are not moving. Let's say they're is already the solution of the Hamiltonian self, whatever it is. So we're upgrading and downgrading this order parameter from order parameter to wave function back and forth, but bear with me. Yeah, it might. I haven't seen his lectures, but it might resemble that. So of course the time derivative there is interesting because I want to find if there is some non-trivial current effect through it, and that will give me a rate of charge, some charge flow, as you're already thinking about. So let's write down this size again in terms of magnitudes and phases. So for each one of them, now it's interesting to write as the square root of the density in the respective superconductor, right? Before I was writing psi square is equal to superfluid density, but now I'm doing on the other way around, times its respective phase. And if you notice, these equations are rather equivalent. You just take 1 to 2, so we can just work out one of them and we get both in the end. So the time derivative will act now both on the density and in the phase. For the density, we have the 1 over square root. Let's keep a generic index. And the time derivative also acts on the phase itself. So and that is trivially equal to, let's say, the potential in that side, which will be plus or minus 2. Plus the tunneling rate now for the other superconductor. So I won't do anything very complicated. You can just multiply by square root of n and e to the minus I theta. So we get a dot plus I a dot goes to the potential on that side, and A plus the tunneling rate times now the difference in phase between one superconductor and another. And the result over 2. So this is nothing but cosine So when we have a complex equation like this, it's usually worth it to separate real and imaginary parts. So from the real part, we get this minus r a dot equal to the real part there. And for the imaginary part, we get the first term. So what we can do now is to plug back the ones and twos and see if we get something non-trivial, right? Because in principle the equations are the same, so for both of them. Yes. Yes, there is a chain, there is a flow, but note that this is a circuit, so things can be compensated such that the value at any given time, right? Not a bottomless, almost a bottomless course of. Oh, sorry, maybe I was not clear. So this is essentially U1 and this is U2. Yes. Just to write the equations, not to write everything twice. Good. So then we can get from the imaginary part the rate of change in density, one side or another. So for one, for the superconductor on the left, we get 2k h bar, square root of the densities on each side, times the sign. Let's now define delta as the difference in phase from 2 to 1. Because if I'm writing the equation for 1, this is 2 minus 1. This. And if I would write the equation for 2, the only difference is that I invert the order here inside the sign. So then I get a minus overall sign. So this is minus dot. What makes sense, because whatever is coming out from one side is getting to the other, right? In some sense, the flow from one side just getting through the junction. So check, sanity check. Good. Now there is also a rate of change in the phase. For the first one, now let's write both separately. Now it comes as the cosine of this phase difference minus with the minus here from the other side, that's right. And I'm using for U1 QV over 2. Yes, over H bar. And one can use the same but now the potential is the opposite, right? I decided to write in the symmetric setup. Now something interesting, we can get two interesting things. So we can really relate this first finding of the rate of change of the density with the current flow. Kind of the phase difference, but the phase difference itself changes with time. So we can write from these two guys that delta dot is delta 2 dot minus delta 1 dot which is Q over H bar, meaning it evolves linearly with temperature in this fixed potential scheme. Now if we plug this in the current equation, we get something interesting, which the phase difference at a given starting point in time, but with an associated, one can think of a frequency, so we can call this Josephson frequency. So yes. Yes, I can. Maybe I said that in the beginning. Can assume that these are really the same type of material that you just cut in half and sandwich an insulator in between. So then we can already get out of this result two interesting and a bit spooky things. First is the DC Josephson effect, meaning if you apply, if you don't apply any voltage, this current is still finite if the phase difference between the superconductors is non-zero. So you get some flow of particles for free just by really put superconductors together. So even for V equals to 0, J is equal to, call this some J naught, some constant. Times the sign of the phase difference between the superconductors. Yes. Yes, so to connect with something we talked about yesterday, perhaps. So if the fact that the phase is changing, here it's happening rather abruptly in this very simplified picture I showed you, right? But you can actually think that there is a phase gradient. And yesterday we mentioned that this phase gradient is associated with the idea of a superfluid velocity. So in this case, where things would look rather discontinuous, it's just really the numerical difference. But if you go to a more detailed approach to understand these and really look at the wave function, how it changes and how its phase changes across the junction, would be something continuous that you can associate a gradient to, therefore some velocity, the same way as we did yesterday. Yes, so this goes back to something related with this invariance to the phase, because again, in principle, we are solving the problem, and if you are just interested at the energetics, there is nothing in the energetics that tells me that one phase is better than the other, because I'm just interested in the magnitude, right? But in principle, if you cool down one piece of material here, and the same kind of material, but physically separate such that their wave functions cannot talk to each other, they will develop an order with a specific phase, which if you don't put them together, it's almost irrelevant which phase they are, because all the thermodynamic properties will be the same. Now the magic is when you put them together, and then the phase differences become important and act as if you have really well, it's literally here a barrier that really changes both the magnitude and also the phase across this barrier in a non-trivial way, creating a gradient that we can associate with a velocity. I don't know if that answers. It clarifies a bit. It's because you can essentially think that you're cooling down these two chunks of superconductors independently, and they define their own ordered state with their own associated. The second interesting thing is the AC version of it, which comes about if we apply a voltage which is constant in time, is not oscillating, and then what you get of it is a current that actually oscillates in time with this given frequency. And is this frequency, I mean, Q over H bar is actually a rather small number, right? I didn't give you a number perhaps, but this is essentially the flux quanta. So it's something like of the order of 10 to the minus 15 for the flux in Tesla. So it's rather small. If you have something oscillating really fast, because it oscillates with a small frequency, what do you get on average if something oscillates very fast? If you average over a slice of time, something that is, you get 0, right? So it's almost funny that if you apply a voltage, and let's say your electronics is not as fast as this frequency, you actually see 0 current on average. So it's almost on the other way around. So it can be that the average current is 0 once you apply voltage, but if you don't apply voltage, then you get a current. So it's very counterintuitive, this qualitative. So if I understand that clock correctly, have 10 more minutes. So I'll just touch upon the squid story. And as a side joke, that's what you get if you Google squids. But that's not the squid we're going to talk about. They look like this. And this stands for, as I mentioned in the first class, superconducting quantum interference device. Right? So if you're doing interference, you usually want two paths and some sort of phase mismatch after you meet. So that's essentially what we are doing, but now with the current. So this is the material itself, whatever is in the blue, grayish color, you should understand as a superconductor. And the white things in between are two Josephson junctions, one in each side of the loop. So essentially, just by charge conservation, we want the total current to be equal to the sum of the currents. And in principle, if we look just at the Josephson junctions themselves, we would get a current which would be proportional, let's say, to the phase difference from one superconductor to another. And each junction here could have its own phase difference. Could be a delta A for the top one and a delta B for the bottom one. But now, on top of this phase that we get because of the junction itself, there is also the phase associated with the loop. And that's, again, intrinsically related to the flux across this loop. So how can we account or put all these things together? So I'll keep this complete later. But essentially, one can think about the changing phase through the upper loop, or let's call the A path through the top, which will have the intrinsic phase change for the superconducting junction, which I'll give you ad hoc, but also an associated phase of this wave function that comes from the flux through the loop. And it comes here in this fashion. Actually, we can go one step back and really take the line integral of the phase of my order parameter through loop, whatever it is. But we learned from the flux quantization part that we can, quote unquote, replace the changing phase by the vector potential interchangeably in this gauge we chose. So we can do that through the A path. And we can do the same and analyze what's the changing phase going through the other part of the loop. We'll have the phase associated with the junction, but again, the phase associated with the path. Now again, if you think about a big single-valued, a macroscopic single-valued wave function on the right corner there, it should not matter where you how you get there. It should matter that the phase get at this point is the same. Doesn't matter if you go through the top, the bottom, right? So something that you get by making this phase difference to through the different paths the same is that the difference in the phases between from these two junctions is actually controlled by the flux you're passing through this loop. So this probably looks, I'm afraid I'm a bit fast because I want to make a comment soon. Now going back to the currents, if we now use these relations between the phases across the two Josephson junctions in each side of the loop. I'm going from current density to current, but just multiply by the area, cross-sectional area, should be fine. So if I assume the junctions to be geometrically similar, I have a constant, and again, the sign of delta A if I don't apply any voltage. And for the second one, essentially the sign of the phase change across the junction for the B junction. But then I can use this relation to introduce actually the magnetic field explicitly on the dependence of this current. And what we get is essentially some constant. So let me call this some not prime times the cosine actually of of how many flux quanta are actually there passing through this. So it's really and this oscillation of the current as a function of the field is what actually makes this a very good sensor for magnetic fields, which are very, very tiny, because now you have oscillations which are controlled by the magnetic flux quanta, which is essentially the smallest magnetic flux one can get, which is of the order of 10 to the minus 15 Tesla. And if you apply a magnetic field and you measure your current, what you see is that your current, well, the absolute value of the current oscillates with this spacing between the maxima of the order of 10 to the minus 15 Tesla. So it's very easy to identify maxima in a measurement. You take derivatives, and so then this allows you to get very precise magnetic measurements with something of the order of 10 to the minus 18 Tesla days, which is quite remarkable. So this kind of structure is the core of this kind of technology, of squid technologies. And I mentioned the first lecture too, that this is also related to this idea of quantum computation. And I apologize, I don't have much time to tell you about that. Maybe you can ask me later, or I can suggest you some interesting reading on that you can easily get out of what you heard here today. Or this. All right, and with that, I will stop.
In order to get the first and second equation of Ginsburg-Landau, we minimize the free energy. That's right. Can you say something about this? Is this free energy something like the Lagrangian? And I don't know. Classically, we minimize the Lagrangian, right? And it's the action. So what is the connection?
Yeah, so I think these things become really evident if you write things in a path integral formalism. So then you can really get your partition function out of a path integral, which is an exponential of the integrals of action, and inside the action you have the Lagrangian. Maybe you heard about this this week. So yeah, so this is a rather phenomenological expansion out of something that you can construct like that. So you can get your partition function out of your Lagrangian. and then define a free energy as minus kBT ln of the partition function, and do essentially thermodynamics out of that.
So following up with the previous question, so this is all very phenomenological. For example, if you want to solve for the parameters that I was asking about, the A and B, if you try to use the C, then you have to calculate the specific the specific heat, right? The heat capacity. And I imagine that you would do that by using the free energy, right? But
Yes.
that, do you use the same formulas for this the heat capacity in terms of the free energy as if that was the statistical mechanical free energy?
Yes.
And how do you I mean, if these free energies, because it seems like you're just minimizing something.
Yeah, I think maybe the jump of the cat is that you need temperature to talk about thermodynamics, find specific heat. And in principle, maybe when we talk about minimization, you just think, oh, I want to find the ground state of something. But there is a version of this kind of calculations that encodes temperature, and then that can be done systematically. And then that will be very different if you think they're bosons or fermions and so on, but that's brighter, favorite model, and you can get other systems.
How can you measure the phase of a superconductor?
You cannot. You can see if there is a phase difference, but the absolute value of the phase is something. That's So in some sense, the fact that you can measure phase difference gives some reality to the phase itself. So all the fact that we observe kind of physics, kind of weird currents that depends on phase difference, is some kind of measure of the phase, but not absolute measure of the
I would like to ask you about the vortex structure. You show here a picture from this lattice.
Yeah.
And here you have this structure, but I was wondering, I don't know what determines this structure, like the size of this lattice, and if there are other options, not hexagonal, but I don't know, cubic or something. I don't know.
Yeah, so in some sense you can really think electrostatically instead of thinking about flux tubes that actually would have some force between them, right? Because they're threads of magnetic field, you can just replace them by point chargers. Then if you have point charges in space and they interact with rather long range interaction, actually that's the kind of lattice you get. That's a kind of Wigner lattice, really hexagonal, because you want everybody to be far from everybody else as possible, and really the energetics works out for the hexagonal. Yeah, that's.
Why is the J the total current, the time derivative of the n's? What were these n's again?
Sorry. So n is essentially a measure of superconducting density on one side or another. So if this is changing over time, that it's going from this first superconductor somewhere, and in this case it's going across the junction. That directly gives to the junction. So I'm just boldly associating rate of change of density one side to another current.
Earlier, you said that the BCS theory and this Lindsberg-Landau theory could explain conventional superconductors. But are conventional superconductors any of those branches that you said, or and what would be unconventional
Yeah.
superconductivity?
So the elemental materials are usually conventional, with no exception. The fluorides, the ones with the balls, the soccer balls, they also seem to be conventional, in the sense that they are mostly driven by electron phonon interactions, are rather isotropic and featureless and something. All the other ones, the cuprates, the iron-based, and heavy fermions, they are within realm of strongly correlated systems, and these materials are more complicated because not only superconducting, other phases of matter coexist or compete the same phase diagram. So then other orders and fluctuations of this order can actually rise to the unconventional character of this. So then the pairing mechanism is not phononic. Really the other parameter is tropic and dynamic.
But in these conventional branches, this theory could predict them or actually understand them?
I would say understand. Predict an overstatement. In some sense, BCS predicts that any boring metal superconducts. So yeah, and I showed, maybe there was a table, and most of the elements actually do. Exceptions, just the fact that we didn't get to low enough.
Thank you.
Maybe this is too basic, but why does copper, silver, and